Hello and welcome, Dr. Schneidley speaking, and even though today we have a lot to do with groups in pyramidal forms, I must admit that I'd rather do some holiday similar to what the captain does. Therefore, I shall introduce you to my assistant. He's called, who cares, he's just the assistant. Come here, and implement groups, will ya? Hello, Mr. Schneidley, here's your coffee that you... Mr. Schneidley, hello? Hello? Well, the last thing I heard was that he wanted me to implement groups, and I guess I will just get started with that. Finally, I can show what I'm actually capable of. As usual, I will turn my head to the left just to learn from how it's done. A group seems to be something that is intersectable and that contains a bunch of children. And yeah, that's pretty much it. In our case, the children are also intersectable objects, mostly either scenes or other groups. Makes sense. On top of that, the Ceepepporg version will use the heap quite intensively because every scene or every intersectable there, which they call scene, will have to be on the heap in order to get that pointer that they require to make the dynamic dispatch work. See the intersect call there? Yes, that's a dynamic dispatch. And to my mind, that's quite expensive, both when setting up the data structure and secondly, when making the calls. Also, they use a list, which is fast for insertions at any place, but slow for actually iterating over it. So I'm not quite sure why this happens and why they think this is required. So yeah, that will be better as a vector, but hey, who am I to say that, right? We will use a vector, that's for sure. Something we will also do, or better not do, is to use dynamic dispatch here, because we exactly know what kind of objects we are going to store, and that it's only be able to be two things. Either it's a sphere or it's a group of spheres, right? So why not preset this and use generics instead? That way there's no dynamic dispatch and no need to heap allocate any single sphere that we have, and I guess there might be thousands of them at the end of this. At the very basis of our implementation is a pair, which is really just that, a generic pair of two things. In our case, it's an item and a group. The item is usually a sphere. Well, not usually, probably always. The type group is the interesting type because it has an own bound, which is supposed to be able to use or do distance measurings with rays. And it has a bunch of children, which is a vector of a pair of items and type groups. You see that there, it's kind of fancy, lots of nesting going on in the type declaration, but yeah, that's standard Rust, I guess. Nothing special, nothing fancy either. In C++, this would look a little bit different, more complex, more difficult to read, but in Rust it's just idiomatic, I think. And that's pretty much it. Distance measure, or the bound that is supposed to be an item that can do distance measurings, is just used to be able to quickly assert if array is actually hitting the group without traversing all the children. This is interesting when doing the intersection with the group, as you see there. Self-bound distance from array, that's basically a quick way to say, oh, we are being hit, or we are not being hit. Then the only thing that's left to be done here is to iterate all of our children and intersect them. Interestingly, because we don't have dynamic dispatch here, we will basically have to match the actual type of the item and then call the intersect method specifically. As you can see, it looks kind of redundant, but you know, we don't have dynamic dispatch, so we chose static dispatch. This is why we have to do it exactly like that. When testing, I encountered this little syntactical gem that happened to revolve around lists of tuples, which can come in handy when you want to make your code less redundant and traverse a bunch of records basically to do the testing for you. As you can see, I'm trying to decompose the tuples again in the for loop, or destructure them into their individual parts, but for some reason this was never working. And I couldn't figure out why. The compiler told me that something wrong is happening, and yeah, something. In the end, it turned out that you have to put an ampersand in front of the tuple there on the left side where it's destructured. Otherwise, this just won't work. I still don't really know what the problem really is, but yeah, that's how it has to be done. Then it will magically work. There we go. Now that we have groups that can hold spheres and other groups, we are ready to actually set up such a complex group in the form of a spherical pyramid. This could be easy, but unfortunately we've decided, or Dr. Snidely has decided, to parameterize the floating point type in order to be able to exchange it later, right? This also means that string or float literals are actually not usable anymore. No, it can't be done. And no type conversion that we can type here will actually work, because t is not of type of the primitive float. No, it's a trait float. And literals don't basically convert to a trait, which kind of makes sense, but it also makes it so much more difficult to do any kind of math here which with preset literals. Therefore, in order to make this work, we will have to build our numbers 3 and 12 with float 1 and combinations of these. It's quite incredible, and if it teaches us one thing, then don't generalize your floating point or your number types. Don't, unless you don't ever use literals in your code then in order to implement something. It gets even more interesting when you have to cast an integer type, for instance, to your generalized floating point type. Numcast to the rescue, I say, because there is a specific trait that is implemented by your basic primitives, which allows you to do just that. Basically a trait-based cast. Makes sense to have that, because otherwise you couldn't write that code at all. But of course it doesn't make it easier to encode what you want, right? Compare the numcast syntax to a simple dx as float 32, for instance, that you could write in any other case. Even though the code looks pretty good, I mean, considering I'm just the assistant who used to make coffee, it's difficult to judge if this actually does anything useful, right? I mean, we have kind of copied the code that we've seen on the left side, which is the Go implementation, but who can tell if that will resemble a pyramid at the end? I guess that's something left for the next phase, which shall deal with image generation.
That and more in our next episode of Trace Quest 5.